This video is problem 2 from the 2019 AP Physics C Mechanics free response questions. This is a fun problem. There are a lot of different things going on here. So why don't we slide down and see exactly what's happening. Pass through all of this. Okay, and here we go. We've got a little diagram of what's going on here and a description. And let's go through the description. A pendulum of length L, okay, and we'll kind of mark this up as we go. This is length L. This consists of block 1 of the mass 3m attached to the end of a string. Block 1 is released from rest with the string horizontal as shown above. At the bottom of its swing, block 1 collides with block 2 of mass m, which is initially at rest at the edge of the table of height 2L. Block 1 never touches the table. As a result of the collision, block 2 is launched horizontally from the table, landing on the floor a distance 4L from the base of the table. After the collision, block 1 continues forward and swings up. At its highest point, the string makes an angle theta max to the vertical. Air resistance and friction are negligible. Express all algebraic answers in terms of m, L, and physical constants as appropriate. So what's really going on here is this block is going to swing down. It's going to bump into block 2. And block 2 takes off and finally hits the floor at a distance 4L later. So why don't we get rid of those things there? Okay, and this is kind of like a mini Rube Goldberg. So let's just start in with these different problems. So part A of this is asking us to determine the speed of block 1 at the bottom of its swing just before it makes contact with block 2. So part A is a potential energy to kinetic energy solution where we find the speed of the block using the change in kinetic energy. So why don't we write this out here? In fact, we'll slide down a little bit. So we know that potential energy, the change in potential energy is going to be equal to the change in kinetic energy. And this is just the change in potential energy is going to be m times g times L, where L is the length of the string, and that's going to be equal to 1/2 mv squared. So the m's cancel out here, and what we're left with is velocity squared is equal to 2 times g times L, and the speed of block 1 will be v is going to be equal to root 2 g L. And we're going to be using that later on in the solutions as these things move forward. So we've got the diagram copied here again just for reference. And for part B, on the dot below, which represents block 1, draw and label forces, not components, that act on block 1 just before it makes contact with block 2. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Forces with greater magnitude should be represented by longer vectors. So we're creating a free body diagram for block 1, and the key to this problem is that the block is in circular motion. So the net acceleration is inward, where, in fact, we'll even write this down up on the side here. The net acceleration as this thing travels in its path down like this is going to be inward. And at the very bottom, that acceleration, in order to maintain that circular motion, has to be directly upward. And that acceleration is equal to v squared divided by the radius of the circle. But we know that that's L, so that's going to be equal to v squared divided by L. Now, the forces on the block just before the collision are gravity and the tension force on the string. So for the moment, we'll just draw like a little free body diagram here on the side. So we've got some tension force, some Ft that's pointing up, right? That's what's keeping the block in circular motion. And then there's some gravity, which we'll call Fg, and that's pointing downward. To maintain that net upward acceleration in that position, the tension force pointing up, we've got some acceleration. The net acceleration has to be upward in that direction. So the force associated with that acceleration is going to be the force of the mass of the block times that inward acceleration. So this tension force needs to overcome gravity and provide that upward acceleration. And we only need to draw a diagram without calculated magnitudes. So we just know that the upward force Ft, the tension force, must be greater than the downward force Fg. That's the only way we're going to get a net upward acceleration. And we can show that on our diagram down here as a longer vector for upward for Ft. Now, we're not really doing things like quantitatively here quite yet, so what I'll do is draw an upward arrow representing Ft, and I'm going to draw a shorter downward arrow for Fg. And those are the forces that are acting on the on the block at that point in time. So now we're actually getting into, for part C, let's just read it out. Derive an expression for the tension Ft in the string when the string is vertical, just before block 1 makes contact with block 2. If you need to draw anything other than what you have shown in part B to assist your solution, please use the space below. Okay, they just don't want you messing up the diagram there that you've already done for part B. So we do know that, let's just quickly draw we have our mass for block 1 here, and we've got some upward force, Ft, and we've got some downward force, which is Fg. And we know that we have, in order to have an upward acceleration, we have some net force between those two, and that net force is associated with the circular motion. So if we mathematically combine all of these things, we know that this net upward force is going to be equal to the tension force minus the gravitational force. And what we're looking to solve for here is the tension force. So we're just going to rearrange that a little bit. And this becomes, tension force is now going to be equal to the net force plus the gravitational force. And now we can start substituting some stuff in here. So we know that F sub n, the net force upward, is going to be, that's going to be m times the acceleration. But that, in our particular case, the block is 3m, and the acceleration is v squared divided by L. So we can rewrite some of this, and we also know that the downward force is going to be, just going to be mg, but that in our particular case is going to be 3m times g. And from part 1 that we solved a little earlier, or part A above, what we have is v, the speed of this block 1, is equal to root 2gl, and that means that v squared will be equal to 2gl. So now we're just going to substitute, and what we're going to get is Ft is going to be equal to 3m, we'll do this piece by piece, v squared divided by L plus 3mg, and we'll substitute again, and this becomes 3m, but v squared is equal to 2gl divided by L plus 3mg, and we can see that the L's cancel out here. And what we're left with is Ft is equal to 3m times 2g plus 3mg, and we can simplify that. This becomes 6mg, and the whole thing turns out to be 9mg. So for parts, we have the drawing again here just for reference, but for parts D through G, we're going to use a value for L, and we're going to calculate some hard values. And that length is going to be, L is going to be 75 centimeters. I like to always write that in terms of meters, because if we use the standard units, we're always going to get the right units at the end. Things just take care of themselves in that way. So part D is asking us to calculate the time between the instant block 2 leaves the table and the instant it first contacts the floor. Now, the time for block 2 to reach the floor is just the drop time due to gravity, right? And we know that that is going to be the downward acceleration is going to be minus 9.8 meters per second squared. And we also have, we know an equation. We don't need to derive this out. So if some height or some distance is going to be equal to 1/2 at squared plus initial velocity times t, but our initial velocity in this case is 0. It starts at rest, so this goes to 0. And what we're left with is h is equal to 1/2 at squared. But h is actually a negative value, right, because this is dropping. The height is changing down, and that's 2L. So we know that h is equal to minus 2L, which is going to be equal to minus 1.5 meters. And we have a value for A, so this whole thing becomes minus 1.5 is equal to 1/2 times minus 9.8 t squared. And we solve this out looking for t. T will equal to 2 times 1.5 divided by 9.8, and we take the root of all of that. And when we do that, we come up with, looks like 0.55 seconds. For part E, they're asking us to calculate the speed of block 2 as it leaves the table. So we can't use, this sounds like a conservation of momentum problem, but we can't use conservation of momentum directly to determine the speed of block 2 as it leaves the table, because we don't know the velocity of block 1 right after the collision. But we are given the distance block 2 travels before it hits the floor, and we just calculated the time that it takes for the block to hit the floor. So we're going to use one of the first relationships that we encountered, and this is that some distance in the x direction, some dx, is equal to the velocity in the x direction times the time. So our velocity in the x direction is going to be equal to that sum dx divided by t. But we know that d sub x is equal to 4L, which is going to be equal to 3.0 meters. And we know that our time is equal to 0.55 seconds. So this initial velocity for block 2, we'll call this just Vx. That's going to be 3.0 divided by 0.55. and we're not going to stick too closely to significant figures just to give us some playing room here. And this becomes 5.45 meters per second. And that's the speed of block 2 as it leaves the table. Okay, we're just repeating the drawing here so that we can see everything again. And for part F, they're asking us to calculate the speed of block 1 just after it collides with block 2. Well, now that we have the speed of block 2 after the collision, we can use conservation of momentum to find the speed of block 1 after the collision. And we have an equation and a value for V1 from before. This was the initial speed of block 1, and that was V1 is equal to 2GL. And when we plug values in for that, that's going to be equal to root of 2 times 9.8 times 0.75. And so our initial velocity our initial speed for block 1 is going to be 3.83 meters per second, and we'll need that. And we remember that we'll call this VB, which is going to be for block 2, its velocity, and we remember that that is 5.45 meters per second. So what we have is M1 V1 is going to be equal to M1 VA, and that's the velocity of block 1 after the collision that we don't know. But we have our M2 VB. And we can do some substitutions here because we know that M1 is equal to 3M, and that's V1. And we also know that M1 over here is 3M, and that's VA. And we know that M2 is M VB, and we have a value for that also. But the M's all cancel out here. We don't need those anymore, so we're going to get rid of those. And we can rearrange this particular equation so that we get VA is equal to 3 V1 minus VB divided by 3. And we've got values for V1 over here and VB. So we're just going to plug those values in. And what we get is 3 times 3.83 minus 5.45, and we divide that all by 3, and what we get at the end of all of this is 2.01 meters per second, and that becomes the speed of block 1 just after it collides with block 2. For the last part of this particular problem, they are asking us to calculate the angle theta max that the string makes with the vertical as shown in the original figure when the block 1 is at the highest point after the collision. So let's just slide back up to take a look at that again. What we have here is just a triangle, right? And we can look at this. Oops. We can look at this down here like this. And we can cut that across here. So what we have is the block itself actually continues traveling upward, right, after the collision like this, and it raises up some height. And we're going to solve this. We're going to solve this again using potential energy and kinetic energy relationships to determine how high that went. And once we have that, we have this other remaining triangle that's in here. And we'll write some relationships for this down lower where there's a little bit more room. So we're going to calculate this theta, oops, leave a little bit of space in here. So let's draw kind of a larger triangle for what's going on. Here's how the arc of the block itself. But what we know is that this is going to be the change in height that's due to kinetic energy to potential energy. And we know that this length here is L. That's the initial length of the string. So that tells us that this length in here is going to be L minus H. And this length over here is L again. And what we have inside of here is theta. So we have our physical relationships here, and what we know is that mgh, that's our potential energy, is going to be equal to the change of potential energy is going to be equal to the change in kinetic energy. So what we have is mv squared, and we're solving for h here now, so the m's cancel out. And what we wind up with is that h is equal to v squared divided by 2g. And once we have that, we also know to find the angle that cosine theta is going to be equal to L minus h divided by L. So theta itself will be equal to the inverse cosine of, make that a little clearer, of L minus h divided by L. And now we're just going to plug in some values. We know what we're looking for here, and we have our numbers. So the first thing we're going to find is h, and that's going to be equal to, these are values that we had before. The velocity, the initial velocity of block 1 was 2.01 meters per second. So we have that divided by 2 times g, 9.8. And when we do that math out, we wind up getting 0.206 meters. And so L was 0.75 meters. So now we have L minus h is going to be equal to 0.75 minus 2.06 meters, which is going to be equal to 0.554 meters. And finally, we can find our theta, which is going to be cosine inverse of 0.544. And once again, significant figures, we've kind of played fast and loose with those here. Divided by 0.75, and that's going to be equal to 43.5 degrees. And that's I believe that's the end of problem 2. Yep, that problem 3 comes next. So stay tuned for solutions to other AP Physics free response questions for electromagnetics and mechanics and just the introductory courses. And thanks for watching.